Okay, so we talked about balancing redox reactions. And this is an example from the book that we have that I copied off, and I wanted to do it myself since I didn't understand this part of the chapter. And so let's start. So the first step in balancing the equation is we have to separate both reactions. We have to separate two half reactions. So one is the oxidation, one is a reduction. So here I already did that. So our oxidation is iron and our reduction is CrO7-2. So the next step in balancing the equation, we have to add 1 water molecule for every oxygen. So since here we have 7 oxygens, you can see right here, 7, we have to add 7 waters in order for it to balance out. So now the next step is adding the hydrogen the hydrogen ions to every water. So here we have 14 waters. We don't have 7, we have 14, because 7 times 2 is 14. So I already did that as well. So we are balancing the 14 hydrogen ions with the 14 waters. And this 2 is because we have 2 CRs, and we have to balance that out as well. So, so the next to last is getting the overall equation. So this is the overall. And by doing this we have to, compress both equations to one, and trying to, by canceling out anything that is the same. So for example, if we had 14 hydrogen ions and then 14 hydrogen ions, we would cancel that out. But since we don't have that, we're gonna start with the 6 irons. So we have 6 irons. This is not my writing pen. So we have 6 irons. So we bring that one down, right? So since it doesn't have anything to cancel that with, so we have to bring that down. So we're left with 14 hydrogen ions. So we don't have nothing to cancel that out with as well. So we go on to the next one, which is CR2O7. There's nothing at the top that would cancel it out, so we bring it down too. And then the six electrons were because one side of the equation had more charges than the other one had 6, and the other one had 12. So we are adding 6 electrons. So they canceled out, I think, and we're left with 2Cr plus the 7 waters, that's it. So, in order to get, the last step is to confirm that the whole equation has the same amount of electrons charges, and it is balanced. So, according to the book, this is balanced, so I'm just gonna believe the book and say this is the final answer.
Okay, I'm going to talk about galvanic cells, which is basically an electromechanical cell that derives electrical energy from a redox reaction. So it consists of, right here in my drawing, of 2 metals combined by a wire and changing electrons. So basically, with this little wire right here, they're changing electrons. So it goes from here from left to right, they're changing electrons. Okay? So, just so I can explain a little bit, this one is the zinc. Okay, so it's the metal, it's zinc, and this one is copper. So between these two, the reaction going on here, and because also in the cell bridge you have chloride and and potassium. So you have these two solutions inside, and between the reaction going on here, they're changing electrons. So one electron is moving from the zinc into the copper, so that way it's creating electrical energy. So if we were to right here connect and let's say a bulb, it would turn on because it would be generating electricity for the bulb to turn on. The cell operates on the principle that zinc is being oxidated and copper is being reduced. So this is going to generate the electric energy for the light bulb to turn on, okay? So it can also turn on anything else, but it's generating electricity because of the oxidation and the reduction here.
Okay, so we talked about She batteries. What She stands for is standard hydrogen electrode. So this is one example we're going to use is Zn goes to Zn2 plus the 2 electrons. This is the cell diagram. This is something more simpler than doing the actual battery with your salt bridge and your reactants. So that's just a more simpler way to do it. So we have Zn goes to Zn2 plus. We know that at standard conditions, every substance has 1 mole and it's under 25 degrees Celsius. So that never changes when you have standard conditions. So we have two sticks or two L's. You can see it. That's your salt bridge. And then we are left with hydrogen goes to hydrogen. Hydrogen ion goes to hydrogen. So plus the PT. What is PT? PT provides a surface where reduction takes place. So now we're going to separate this equation into two. We have the oxidation, which is our anode, and our reduction, which is our cathode. And we can find that by using Leo, the line goes GER. L stands for loss, electrons, and that's oxidation. G is gain, and E is electrons, and R is reduction. Okay, so I did the separation of the two equations, so now we're left with canceling out anything that is the same. So we don't have anything that can cancel out with a Zn, so we bring it down. The 2 hydrogens come down because there's nothing we can cancel it out with. Now we have 2 electrons being shared or transferred. Those cancel out and they don't they don't go in the final equation. We have Cn 2 plus. That goes down since there's nothing we can cancel it out with. And finally we have hydrogen. And this is our overall equation. Okay, so we have we talked about EMFs, and this is our equation regarding to EMFs. The E cell equals the the E of the cathode and the E of the anode. So in this example, we have the cathode is 1.23 and the anode is negative 0.44. So when you substitute both numbers, we have to put in since you have a negative here, you have to put it in parentheses. And don't forget that a negative times a negative is a positive. And when you put this into your calculator, do not forget the parentheses. And once we calculate the E cell, we get 1.67 volts.
Okay, next we're going to go ahead and see how an E cell is related to thermodynamics. So such that we're going to go ahead and see the change in free Gibbs energy. Also, a galvanic cell is a change from chemical energy to electrical energy, okay? To do this, electrical energy, like it generates electrical energy like the one to run a motor or to run let's say any device that needs electrical energy. Okay, so we're gonna go ahead and show you two equations that we're gonna go ahead and use for this section. So these are the change in G, okay, which is the change in free energy, equals negative NF E cell. Okay. Also, the other equation we're gonna go ahead and see is E cell equals 0.257, okay, volts over N, okay, and ln K, natural log of K, okay? So these two are the equations we're gonna go ahead and be using for the next example, okay? And we're gonna go ahead and see how to work with these two equations, okay? So I'm gonna go ahead and get my notes so I can go ahead and show you more or less what example we're gonna go ahead and use, okay? So let's say we have this reaction. Okay, so let's aqueous okay, so we're gonna go ahead and have this example, and we want to go ahead and find the equilibrium constant for the following reaction at, I'm gonna go ahead and write it right here, at 25 degrees Celsius, okay? So we're going to find the equilibrium constant for the following equation, okay? So for the following reaction, my bad, okay? So we're going to go ahead and first find the half reaction. So we're going to find the oxidation, okay? Okay, so this one, okay? Gain, lost an electron. Okay, and we're gonna go ahead and see the reduction. Okay, so we're gonna go ahead and see what's next. So we're gonna use that formula we just saw right now. I'm gonna go ahead and get the cathode. Okay, minus the anode. Okay, so the cathode is our this solution right here, the reduction, and our anode is the oxidation. Okay, so we're gonna go ahead and solve for this. So it's gonna be 0.15 volts minus negative 0.14 volts. Okay, so this is gonna give us a total of 0.29 volts for the E cell. Okay, so this is what we have for the volts. Okay, so we're still not done. We still have to calculate the constant. Okay, so I'm gonna go ahead and erase this real quick. Keep in mind that our answer, we got 0.29 volts. Okay, so we're gonna go ahead and use now the other equation because we want to solve for the K constant. Okay, so we're gonna go ahead and switch it around the value. So we're gonna be looking for K constant. Okay, so it's natural log of K equals N E cell over 0.0257 volts. Okay, and if we solve for this, your answer should be E to the 22.6, and this, if you solve it in your calculator, should be 7 10th 9 power. Okay, so this should be your answer right here. This is the K constant for the reaction that we're looking for at 25 degrees.
Okay, so we talked about 18.5, and 18.5 doesn't provide any much information but the Nernst equation, and this is the Nernst equation, which is delta G equals delta G cell plus the rate constant, the temperature, and the log of the quotient. Now the Q is products over reactants, and the Q is equal to the K, which is the equilibrium constant. The E is 0, and we are going to do this problem. And so the book says the CO has 0.15 moles and Fe plus 2 has 0.68 moles. Now, since this equation does not provide, it's not at standard conditions, since we have less than 1 mole on the molecules, we have to use a Nernst equation. So the next step here is finding the oxidation and the cathode, or the oxidation of reaction, which is the anode and the cathode. So our anode is the CO goes to CO2 plus the two electrons. That is our anode. Our cathode is the Fe2 plus the two electrons goes to regular iron. Now remember we talked about the E cell, and the E cell stands for the cathode minus the anode. So we know that by the example provided in the book, we sorry, CO has 0.44 volts, negative 0.00 volts minus the negative 0.28 volts, and that equals to 0.16 volts. 0.16 volts, that's a minus. Okay, so the next step is using the Nernst equation, and we are using a different type of Nernst equation, which is E equals to E cell minus the rate constant of the temperature and the NF, the log of quotient. Now, that is our next step. We have to substitute the numbers. So we know the E cell is 0.16 volts, so we're gonna start with that, which is negative 0.16 volts. And you're always gonna use this number, which is 0.0257 volts over 2. That is our N. And the log of, we're not going to use these numbers, which is the log of, and we said if the Q was products over reagents, so it's 0.15 moles over 0.68 moles. So it's a log of 0.15 over the 0.68. Now to reduce this, we are left with negative 0.16 volts plus 0.019 volts, and that equals to negative 0.14 volts. And this is the Nernst equation.
Okay, so next, we're going to be looking at different types of batteries that we can go ahead and have. So a battery is a galvanic cell or a series of combined galvanic cells that can be used as a source of electric current, okay? So the first battery we're gonna look at, it's a dry cell battery, okay? So the dry cell battery, what it is the basic battery that we everyday use, that we use in our flashlights, that we use in our radios. So it has that cylinder form. So we're gonna go ahead and draw it real quick. So that cylinder form right here. Okay, with that little metal sticking out, which is the plus and the negative. So it's mostly used in like remotes, anything like that. So it consists of a zinc can. So it's what we see right here, and that's in contact with manganese dioxide and electrolyte. Okay, so we're gonna go ahead and get a little more detail on the picture. So we're gonna go ahead and divide the sections. Okay. Okay, so this is your basic dry cell battery. Okay, so this one right here, the first layer is a paper spacer. Okay. Okay, and then the second layer is a moist. It's a moist type of paste that is composed of zinc chloride and NH4Cl. Okay, so this is a paste that consisted of zinc chloride and NHCl. Okay, and the next is this right here, little tube on the center. It's a graphite cathode. Okay, so it's a graphite cathode. Okay, and the bottom right here, it's a zinc anode. Okay, and the combination of all these different types of chemicals are what gives you the electricity when you go ahead and put this little battery into your flashlight, into your remote. This chemical energy converts into electrical energy, and it powers anything that you need at that moment. Okay, so it's one of the, like I said, it's a basic battery. It's the most simple battery that it's a daily used. Okay, so the next one we're gonna go ahead and see is called the mercury battery. Okay, so this one's not as common. It is common, but it's mostly used on medical equipment, okay, and electronic industry. So and electronic industry. So it is a little bit more lasting and more durable than the dry cell battery. So it is a little bit more expensive also because it is because of the components inside. Okay, so it's a little flat figure. You've seen it with the little part on the top. Okay, so it can also be expensive because it's made of stainless steel. Okay, so and also of zinc. So as you can see, a zinc is a very basic component for any battery. So we're gonna go ahead and just give you a little more detail on this battery. Okay, so this is a cathode on the top. Okay, the cathode, which is for all the batteries that have this little thing, think of it as a cathode. Okay, and this, we're gonna go ahead and divide it similar to the other one. Okay, so put this right here. Okay, so inside is a solution. Okay, it's a solution KOH and a paste of zinc OH2. Okay, and also a combination of HGO. Okay, so this paste has a combination of various compounds that go ahead and interact with the zinc on the side. So this one is the anode. Okay, and this around right here, the metal around it, it's the insulation. Most of these components are toxic. You don't want to go ahead and have any direct contact with any of them because they are toxic. they all form together a reaction in order for you to also generate electricity from this battery right here. Okay, so this is the basic components of a normally mercury batteries. Okay, so it has the alkaline electrolytes. Okay, that interact with zinc oxide and mercury oxide. This battery provides a more constant voltage, but and has more capacity and life, like I said. So it's used in medical equipment like pacers, things like that are for a long-term use. So you don't have to be replacing your batteries like the dry cell batteries. Okay. So the next battery we're gonna go ahead and see right here. It's the lead storage battery. So this is the one everybody also knows. It's the one you see in your car. So have you ever if you ever seen you open your hood, you're gonna see a big rectangle there. It's a really big, heavy rectangle. If you haven't tried lifting it, try it. You're gonna have some hard time. Okay, so it's a big rectangle. Okay, with the little exits right here. That when you run out of battery, you just go ahead and plug in these two cables on the positive and negative side, and you can go ahead and have some ignition. Okay, it turns on your battery when you leave the car on, the lights on, and your battery discharges. You connect the wires to these positive negatives, and you get a charge for your battery. Okay, so these are 6 cells joined together in a series. Okay, so each cell has a lead anode and a cathode made of lead dioxide. Okay, so as these little like packets right here has there's like 9 in total. Okay, so all these basically are connected either to the positive or to the negative. Okay, and they're more like negative kind of, they're like plates, but they're connected to either the positive or the negative. Okay, so it's like positive, negative, positive. They go in order like positive, negative, and they have and they both are connected, like I said, to the positive or the negative cathode. Okay, and they're both immersed in an aqueous solution of sulfuric acid. Okay, so if you ever there's a video I run on YouTube that you can go ahead and see when a water jet goes through the cell, and you can see it drops kind of liquid that you don't want to go ahead and again touch because it is toxic. But the constant reaction that the plates have, because the plates are negative, they're filled with these plates are filled with PbO2, so they're lead plates. Okay, so that's why it's called lead battery, and they have a solution inside of H. Okay, so these two compounds react with each other inside your battery, and they can go ahead and give your car energy. So as you can see, this was one of the most powerful batteries that we have. Since it goes in your car, you know you need a lot of electricity to run your car. You know, the radio, your steering pad, any of those things. You need a lot of electricity to run those, even to run your air conditioner, to run your windows down, roll your windows down. You need electricity. So this battery right here, and the reaction between PbO2 and H sulfate goes ahead and gives you a constant and abundance in electrical energy. Okay, and let's go ahead and talk about the two last ones. Okay, so the two last ones are a little bit more complicated and less seen. So actually, one of them it's new relatively. You see it in your phones. It's called the lithium ion. Okay, so it's called the lithium ion battery. Okay, another battery that you've seen and you can go ahead and find in a lot of places, it's a lithium ion battery. Okay, so it's mostly found on your phones. So any phone that you can go ahead and find nowadays has a lithium ion battery. The reason is because they're long lasting, and they're really small, so you can go ahead and fit a lot of energy into a small battery package. That's why you see batteries going smaller every single time, and you see small phones going smaller, because it's a really efficient battery that doesn't need to have such a big space like the lead battery, like the lead battery used for your cars. This one's a little bit smaller, thinner, because it's composed of lithium ions. Okay, so the anode is composed of a conducting carbonious material, usually graphite. Okay, so because it's high reactivity of the metal, a non-aqueous electrolyte must be used. Okay, so that's basically what a lithium ion is. Okay, so that one doesn't really have a like a display picture. You just have to know that as the lithium ions are constantly in reaction with the carbonious material. Okay. Also, we have the fuel cell batteries. Okay, so the fuel cell batteries are the ones it's the ones you can see in any mechanical system. Okay, so a car, it's a fuel cell. Okay, so you need fossil fuels to run this. Okay, it's not the most efficient form of energy. Now the reason is that out of the whole chemical reaction that you're doing with these fossil fuels, the only thing you're getting out of it from electrical energy is 40%. So 60% you're losing it in heat. Okay, or like turning it in vapor, losing it in heat, but everything else, so you only use 40% of that energy you're creating. Okay, so it usually works by converting water into steam, and then that goes into a turbine that drives a generator. Okay, so but it always loses heat, and it's unstable electrical energy. So it doesn't generate as much as we wanted it. Okay, so normally every single fossil fuel, you can say mechanic,
Equation.
Okay, so 18.8 deals with electrolysis, and this is the example for electrolysis or lysis. So the example here is that we have 1.26 amperes or A's is passed through an electrolytic cell containing a dilute sulfuric acid solution for 7.44 hours. And then we're asked to write the half reactions and calculate the volume of the gases generated at STP. So, like any other equation, you have to identify the anode and the cathode by using Leo, the line goes gram, and as we know, L stands for loss, E stands for electrons, and O stands for oxidation, and G stands for gain, E stands for electrons, and R stands for reduction. So that's the way we can identify the anode and the cathode, which is also the oxidation and the reduction. So here, this is our anode and this is our cathode, and we already discussed how we can identify them, so I'm just gonna jump to the next step. So the next step is getting the overall equation, and this is the overall equation, which is 2H2, 2 waters goes to 2 hydrogens plus O2, which this basically turns into two products, and they separate. So so the next step is setting the numbers for the electrolysis treatment. So as we saw in the book and in the example, we know that if the current at the time goes to the columns, or the columns goes to the moles of the electrons, and then from there we go from the moles of the electrons to the moles of oxygen. So here the example provided us that with the current is 1.26, and then the time is 7.44 hours. So in order to be left with only columns, we have to obviously we have to get rid of the other units. So we have A here, cancel with A, seconds cancel with seconds, and hours cancel with hours here. So we're left with columns here. And this is when we calculate everything, when we put it into the calculator, we are left with 3.37 times 10 to the fourth coulombs. So our next step here is to go from coulombs to the moles of excuse me, from the coulombs to the moles of the electron. So we're going to use this number that we said because we are in this step right here. So columns go to the moles of electrons. So we have to use the 3.37 times 10 to the fourth coulombs times 1 mole of electron, because that's what we're looking for. And obviously 1 mole of electrons equals, so 1 mole of electrons equals 96,500 coulombs. So we want to be left with moles of electrons, so we have to cancel out the columns here. So they cancel that, and we're just left with the moles of electrons, which when we put it in the calculator, we are left with 0.349 moles of electrons. So what is the next step? The next step is to convert the moles of electrons, we're in this step now, to the moles of oxygen. And this is where we're at right here. So we are going to use again this number that we just calculated. We're going to put it in front. So we're going to put 349 moles of electrons over 1 mole of oxygen, because that's what we're looking for, divided by the 4 moles of electrons. So 1 mole of oxygen equals 4 moles of electrons. So we're going to cancel these out, and we're left with moles of oxygen, which is right here. So once we calculate that out, we are left with 0.0873 moles of oxygen. So the last step is finding the volume of the gases, and the gas, which is oxygen, at STP given by the equation. So this is our equation for volume, which is the N times the rate constant of the gas and the temperature divided by the pressure. So we are at standard conditions, so our pressure is going to be 1 atmosphere. And that obviously varies if you have atmospheres or torrs or any other unit, but here we are using atmospheres. So what we're going to do here is we are going to use we're going to use this number, which are our moles of oxygen, and the liters per atmosphere divided by the K times the mole, which is 0.0821, and times the temperature, which is standard temperature, is 2.73 Kelvin. So when you're trying to find temperature Kelvin, you have to add 273 to the Fahrenheit to the Celsius to make it Kelvin. That's what it is. So we are at 273 Kelvin standard temperature. So so when we actually put this in the calculator and the calculator does its job, we are left with 1.96 liters for our our electrolysis of sulfuric acid into a diluted sulfuric acid solution.